carry out the research work on MEMS, developing MEMS devices. Here we have the facility to design and develop the design and simulate the MEMS devices. We use various simulation tools to design the MEMS devices, and fabrication, characterization, and packaging we carry out either with foundry support or IIC, Indian Institute of Science, Bangalore. So this is how we are equipped in MEMS technology. I am very happy to welcome you all for this session. We as a group, we are going to explore MEMS technology. I welcome you all with open heart. Hope this training helps you all to explore the technology and to develop many MEMS devices. Welcome you all. So I'm going to start the session now. We will be any queries before starting the session? Okay, then I will, I'm sharing my screen now. Is the screen visible to all? Okay, thank you. So as a part of, as we are aware that we are undergoing a training program on MEMS to develop eventually a MEMS device, which is going to be fabricated at Science Foundry with support of IEEE and ISSS. Thanks to Dr. Veda Sandeep Nagaraj from Tyndall National Institute for giving us this platform to explore the technology. With this, I will proceed with the sessions. So before understanding really what is MEMS, let's have a imagination, or let's have a thinking started on MEMS technology with a very good example. I wanted to take an example of a microphone. We all have seen the stage performance, anchoring, and anchoring on the stage. Whenever we do anchoring on the stage, we will hold a mic. So can anyone tell me what is the purpose of mic over there? Why do we use microphone on the stage? Anyone can answer? I want the session to be interactive so that most of the knowledge gets transferred.
For amplification.
Sorry?
Sound amplification.
Sound amplification. So whatever the person talks, if I talk in a room, 1 or 2 people can hear. If I talk on the stage, I want thousands of audience to hear it, and I want my voice to be amplified. So there is a device which amplifies. And can we imagine the size of the microphone that we hold? It is really huge, right? Now, the same microphone has been integrated to your mobile phone. Yes or no? Mobile phones also has microphone integrated, but
Yes,
can you
yes,
imagine that huge microphone getting integrated to your mobile phone, carrying it all the time around us? It is just such a tedious work to do that. We would have preferred not to use mobile phones itself, right? But thanks to MEMS technology, the functionality of microphone has been retained by shrinking the size of the microphone. So now the microphone size has been shrunk to a micrometer range. And what is expected, the microphone should receive the sound signal, convert it into electrical signal, amplify it, noise reduction, all the signal processing conditioning has been done to the voice signal, and the device is capable of successfully doing it even though it is shrink to the micrometer size. That is the beauty, and that is the achievement provided to us by MEMS technology. There are more than 1,000 devices that are connected to our mobile phones. Still, the mobile phone is handy, right? We can hold the mobile phone in our hand. This is all because of MEMS technology. So if we understand what is MEMS technology, we are also able to contribute towards it. So with this small introduction about the MEMS, let's get into understanding what is MEMS, right? So sorry for this. So MEMS stands for micro electromechanical system. As the name itself is very introductory, right? It is very friendly for us to understand what is micro electromechanical system. Micro stands for the size of the device. So micro, it is 10 power minus 6 meter, micrometer. So the devices are going to be in micrometer size. When I tell micro, it is the thickness of the device, right? Thickness of the layer that we are going to deposit on the to develop the device. And the area of the device can be within 1 mm to 10 mm. So within this area, we are going to develop either a sensor, we are going to develop or actuators. So that is the advantage of MEMS technology. So micro stands for the size of the device, which is 10 power minus 6 meter. Electromechanical tells us that the device is capable of coupling two physics at a time, right? So whenever I talk about electronics, what are the parameters we understand in electronics? It is either voltage, current, resistance, or capacitance. Whenever I talk about mechanical, it is always the gears, the cantilever beams. You apply pressure on the beam will deflect, it will rotate. So these are the mechanical parameters. Now, I am going to develop a device which is going to integrate these two concepts. It is going to have a beam which deflects on the application of pressure. Also, it is going to provide me either the change in capacitance or change in voltage or change in resistance. So electromechanical means two physics are combined together to develop the device. Now, no more the electromechanical concept occurs. There are multiple physics that can be applied. You can also understand the change in temperature. You can also study about the fluid flow, how the fluid flows and how the current varies. That is called as microfluidics. But overall, the name is being notified as micro electromechanical system. And then system stands for the integration of MEMS is not only about developing sensors or actuators. It is about constructing a complete system where the sensor is integrated with the electronic circuits. Now, suppose if I have a sensor which is able to capture the pressure and it is able to convert the pressure into the equivalent electrical signal. Now, this electrical signal alone will not be taken as a system output. Instead, this electrical output will be connected to an electronic system which will amplify denoising effects can be implemented. So a MEMS is a complete system where the mechanical elements are connected to the electronics system. So that is why there is a statement written that micro electromechanical systems, they are the tiny devices which which can integrate mechanical elements, your sensors, your actuators, electronics, all these are integrated on a silicon substrate. Now, why silicon? Why should we go only on silicon substrate? Is there any answer? Why MEMS are developed on silicon substrate?
Availability. Yes.
Very good. It can be because of abundance availability of silicon substrate, but there is one particular answer for this, why we usually go on silicon substrate.
Micro
So you,
machining.
yeah. Because MEMS devices undergo micro machining. Micro machining is equivalent to the fabrication of CMOS devices. If we are from EC background, we understand how our CMOS transistors are fabricated. On a similar manner, the mechanical elements are fabricated. Usually, mechanical devices are either they are drilled, or they are teared. So there are many other machining techniques. But in MEMS, we follow microfabrication technique, which are very, very similar to our CMOS transistor fabrication technique. So another very important understanding why we go for silicon substrate is that eventually, as I told, the MEMS devices has to be connected to the electronics. So electronics are usually CMOS devices. CMOS devices are CMOS devices are
Hello, madam.
Hello, madam.
Hello.
Hello, Professor. I think madam is disconnected.
Yes, sir. Yes, maybe. You have to wait.
Yes, sir. Yes, sir. Sure, sir.
Am I audible to all?
Yes,
Yes,
ma'am.
ma'am.
You are on.
Uh, was my presentation on flow, or it did stop somewhere
No,
in the
madam, it
beginning?
is stopped, ma'am.
From where?
First slide itself, madam.
1 second, sir. Sorry for that. 1 second. Is my screen visible?
Yes, madam.
So
Yes,
I was
madam.
talking about MEMS technology. Was it
Yes, madam. Yes, madam.
delivered?
Yes, yes.
Okay. I was talking about the sensors.
Ah, yes, madam. You have started about that fabrication, about that silicon.
Okay, sir. So I was asking about the silicon substrate, and I answered that the silicon substrate is used as a common platform for MEMS devices and CMOS devices. Eventually, we have to integrate MEMS devices with we have to integrate MEMS devices with the electronics, and electronics are usually our CMOS transistors. So CMOS transistors are developed on silicon substrate. So to have a common platform between MEMS and CMOS circuitries, we go with silicon substrate. So mechanical elements, which was meant to be drilled which was meant to be cutting, and all those other techniques were used to machining the MEMS mechanical elements, are now being fabricated because of ease for developing the MEMS along with the electronics. Then I was talking about the sensors that has been developed on in Center for Nanomaterials and MEMS, NMIT Bangalore. We have developed a thermal actuator. So actuator is the exact opposite of sensors. Sensors usually sense the physical quantities like temperature, sound, pressure. It senses the physical quantities, and it converts them into the equivalent electrical signal, so that the electrical signals can be further processed. Whereas actuators convert the electrical quantity into the physical quantity, like our motor. Motor is an example of actuator. It rotates based on the electrical signal applied to it. So thermal actuator is one kind of actuator which produces change in temperature based on the applied electrical signal. And also we developed the varactor, which is a variable capacitor. These two sensors were fabricated as a part of first community chip activity that was initiated in India. Then we also developed a MEMS microphone for hearing aid application. It is a MEMS microphone, so the size of the device is in micron range. This particular sensor was developed as a part of DST funding. We got around 46 lakh to develop this particular sensor. And then micromotors, it is again an actuator. Micromotors were developed as a part of second community chip activity, and also directional microphone. We can see the complete packaged device being displayed. Actually, there is a microphone inside the package, and this has been developed as a part of third community chip activity. MEMS gyroscope. Uh, Gyroscope is a device which can sense the rotational change in the rotation of a body. We also developed a MEMS microphone for gunshot detection. Recently, we got a project from DRDO Pune. There was a requirement to develop a MEMS microphone to detect the gunshot detection, which will be mounted on the soldier's shoulder, and it will be capable of detecting the direction of the gunshot. So again, we got around 25 lakh funding for this particular device development. Also, we work on MEMS accelerometers. MEMS accelerometers can detect the change in the linear motion. So most of the automobiles are equipped with MEMS accelerometer and gyroscope, also with MEMS microphone. So these are the few sensors that are being developed by our center. So having understanding what is MEMS technology, let's see why we have to really concentrate and involve ourselves in MEMS technology, why it is very important for our students to understand what is MEMS. For that, we have to understand what is the global MEMS market. So if we take a time span of 2030, now in 2022, the amount of billion dollars invested in MEMS market is around 28.6 billion, whereas after 10 years, it will be $64.15 billion. So we can see that there is a gradual increment in the investment in the MEMS market. Also, when we particularly see the market in MEMS sensor, so MEMS sensor will be having a leap from 16.51 billion to 24.74 billion. That is, out of 64 billion, $24 billion will be exclusively for MEMS sensor. So if we are equipped with developing MEMS sensors, it will be a great advantage in near future. And if we can see here, the fastest growth that has been happening in developing MEMS sensor is in the Asia Pacific region, and the country that has been involved in developing this is our India. So it is very important for us to equip with MEMS technology, understanding it, developing more MEMS sensors to contribute to this particular growth. All are comfortable till here? Can I proceed?
Yes, ma'am.
Yes,
Thank
ma'am.
Yeah, thank you. So, what ignites us, what enlightens us to develop MEMS devices is the four key characteristics of MEMS. So the first characteristic of MEMS is miniaturization. A very good example we have taken in the beginning of the section is the microphone on stage and microphone on in mobile, right? So there is a huge size variation between both the microphones, but the functionalities and the specifications are remain same. So miniaturization is a very important key characteristic of the MEMS devices. As I informed, the size of the MEMS devices, the area varies from 1 mm to 10 mm, whereas the thickness are 1 micrometer to 25 to 30 micrometer. Okay, the thickness of the MEMS devices depends on the foundry that you give. So the foundry decides the thickness of the layer, and it can vary from 1 micrometer to 30 micrometer in size. That is your thickness. The second key characteristic of your MEMS devices is the integration. As I already informed that in MEMS devices will have the mechanical parts like your gears, levers, beams, and these mechanical parts are integrated with electronic circuits, which enables the complexity of the device. And then the next is the batch fabrication. What happens is, if I want to develop a MEMS sensor, I have to contact the foundries. I have to deliver my device to foundries. Now the foundry cannot go with a single device fabrication, because in a single wafer, 4-inch silicon wafer, we can fabricate almost 100 to 150 sensors. So when I have to develop a single sensor, I have to go through the same procedure. Even after if I have to develop 100 to 150 sensor, I have to go through the same procedure. So going with one device development at a time is a waste of time, waste of money, and it is not recommended to develop a single device at a time. So we go for batch fabrication. In batch fabrication, what happens? A single wafer can produce around 100 to 150 150 sensors, so in a single go, but that is which will enable reducing in cost. It produces large volume devices, so that is called as batch production. And low power consumption. As we all know, as the device size shrinks, the requirement of power to enable it also reduces, and it increases the portability, and integration becomes easier. So the four key characteristics of MEMS, why we have to go towards MEMS technology, is one is miniaturization, integration, batch fabrication, and power consumption. Having understood the characteristic of MEMS, we will understand what I can really produce, what I can really work on MEMS technology, right? So what you can develop using MEMS technology is you can develop sensors. As sensors explained, it converts the physical quantity such as pressure, acceleration, temperature into electrical signal. I can also develop actuators. Actuators convert the electrical signal into the mechanical motions, again like pressure, acceleration, temperature. I can develop electronic signal circuitries, microelectronics, right? Like amplifiers, oscillators. Uh, um, these circuits can be developed, and also the mechanical structures like tiny gears, cantilever beams, springs. All these can be developed using your MEMS technology. So as on whole, when do I call it as a system is when I try to integrate microsensors, micro actuators, microstructures, and microelectronics on a single wafer. On a single wafer, if I try to integrate all these four components, then I call it as a MEMS system, right? So what are the applications? Where can I concentrate on developing the MEMS devices? The applications are huge. I have just shrinked to a very minimal application of MEMS. It can be automotive. Airbag deploy system as our MEMS accelerometer. So whenever we travel through our automotives, if there is any pond accident, we can see that there is a deployment of airbag which protects us from damaging from the accident. This is due to the MEMS accelerometers integrated, because MEMS accelerometer can measure the speed of the automotive. If the speed increases beyond the threshold, then this accelerometer triggers the airbag, and that is how the airbag gets deployed. We can also develop tire pressure sensors. Usually what happens when we go for long riding, the tire can get punctured, and we will be unaware of the punctures. So this can be sorted by having a pressure sensor. So this pressure sensor, what it will do, it will try to measure the pressure that is being developed by the tires. When the tire gets punctured, the pressure will be eventually reducing. So if the tire pressure reduces beyond a particular threshold value, then this sensor will alert the driver. So these are the major two examples in the automotive. Also in the automotive, we use MEMS gyroscope. If there is any tiltation of automotive, if the tiltation is beyond the threshold value, which indicates the accident or damage of the automotive, and then that is being detected by our MEMS gyroscope. Even in healthcare, we have the MEMS devices. The very recent and trending research is going on is lab-on-chip devices, where a single wafer will have the monitoring capability. We also have now capsules with micro cameras and drug delivery systems, and these are due to the MEMS technology emergence, right? So micro pumps are the pumps which can deliver the drugs into the body. So they are also in micron range, and whenever you develop microfluidic devices that comes under microfluidic science, but they are also a part of MEMS. Consumer electronics, MEMS gyroscopes and accelerometers are used in our smartphones. So whenever we try to tilt our phone, the camera pops up, right? That is because of the gyroscopes and accelerometers which are trying to trigger the cameras. Microphones are very helpful in smartphones, which allows us to talk to the person that we are in communication. Under telecommunication, the switches, MEMS switches, micro mirrors are used in telecommunication. Aerospace domain, inertial navigation system. Inertial, it will have the integration of both accelerometers and gyroscopes. A single device will be capable of sensing the linear motion and the tiltation. Pressure sensors are very much useful for flight instruments. So these are the various applications. They are not limited to this. They are much more than what I have mentioned, but this is required to us to understand the initial stages of MEMS application. So now, having understood what is MEMS and how MEMS devices are useful to our society and what is the market of MEMS, we will understand what is the development phases that we have to go through in order to develop a successful MEMS devices. So initially, when you want to start with developing a MEMS device, you have to actually understand what is the application of the device that you are going to develop. Is it going to sense the sound? Is it going to sense the motion of a body, or it is going to sense the rotation of the body? So we need to understand where exactly we are going to deploy our particular sensor. So you need to understand the device specification. What is the input pressure? Is the input temperature? Do I have to convert the pressure to electrical signal, or do I have to convert the pressure to capacitance? So the complete insight of the device should be understood. After you understand the device specification, we need to work on modeling the device. You need to understand what should be the mechanical elements that needs to be integrated. You need to understand how to integrate the mechanical elements with the electrical components. So modeling is very much required. After modeling, after modeling and understanding the device dimensions, we are going to simulate the device. Why we are going for simulation is that, as I told, for going into the fabrication, we require batch production, right? Batch fabrication. And each batch fabrication requires an amount of nearly 10 lakh rupees. Recently, I developed a MEMS microphone for gunshot event for ARD DRDO Pune. And for a single wafer production, it cost me around 10 lakhs. So if I go directly through modeling and directly to the fabrication, sometimes it might happen that the required specification doesn't meet. So what I'm doing, I'm wasting my 10 lakh rupees without confirming whether the device is really satisfying my specification. So to avoid the waste of money and the time, because usually projects has a time span of 2 years or 3 years. So one fabrication takes around 6 months to 8 months. So I'm going to waste also my 6 months to 8 months in developing a wrong sensor. So wasting the money, wasting the time, and not understanding how to satisfy the specification. So all these confusions can be avoided if we really simulate the device, optimize the device for the required specification. After the simulation results and modeling results satisfies with the design specification, then we can go for fabrication, right? So the very first stage of our MEMS device development is modeling and simulation. There are various tools available for simulation. Very commonly used in India is COMSOL multiphysics tool, ANSYS tool. So these two tools are very much user friendly. They allow you to understand the implementation of MEMS devices. There is also a tool called Coventaware tool. Coventaware tool is fabrication friendly. It gives you a step-by-step development analysis in terms of fabrication. How really you are going to fabricate the device will be understood by using the Coventaware tool. So usually what we do, we model the device, we simulate the device first using COMSOL multiphysics tool. We apply all the physics, understand the outcome of the device. After we simulate it using COMSOL multiphysics tool and we finalize the dimension of the device, we use Coventaware tool to understand whether the material characteristic and fabrication process really supports the device to meet the specification. After this, the second step is to generate the GUI file. GUI file is like an image. I hope everybody would have seen the analog camera before the digital camera emerged. There was a analog camera where you used to have the negative reels inserted in the camera and used to click the photos, and the negative was before it was in the black color shade. After you click, the images used to become transparent, right? Or everybody would have experienced that. Am I clear with the talk? All are comfortable understanding?
Yes, ma'am.
Okay, so similar manner, now whatever we simulate, we cannot give the simulated structure to the fabricator. Instead, it should be in the image file format. Okay, that is called as GUI, GDS2 file. Okay, GDS2 file has to be given to the foundries to fabricate. So the simulated dimension has to be converted into GDS2 format, and that is called as GUI file. And there is a tool called Clevin tool. In this training session, we are also going to teach you all how to use Clevin tool to finally generate a GDS2 file. So this GDS2 file is what we are going to provide to the fabricator or foundry to develop the MEMS devices. As a designer, my job ends here. I have given the GUI file to my foundry. Now the foundry takes care of fabrication. It uses its process flow. So whenever you design your device, you cannot directly take some random structure and develop the device. You need to understand what is the process flow you want to choose that is being provided by the foundry. I will explain you all what is the process flow. But we need to understand that before designing any MEMS devices, we need to understand the process flow that a foundry is going to carry out while fabrication. So after fabrication, we go for the next step, which is called as wafer level characterization. Wafer level characterization gives us a fair understanding of whether the device is working according to the design and simulated results. Okay, so after that we go for packaging. You all can see the MEMS microphone being mounted on a base. Okay, it is a 8-pin package. the device is being mounted on the package, and there will be a cap which has been which will act as a head of the sensor. So the microphone will be completely packaged as I showed in the first slide. This is the complete package of a MEMS microphone. So after fabrication, then we go for device characterization. Device characterization helps us to understand whether my sensor is working according to the design and simulation. After device characterization, so foundry will fabricate the device. It is not responsible of foundry to perform wafer level characterization and packaging. We have to take it for packaging. We have to characterize the device. So our work starts after fabrication, that is packaging the sensor, device level characterization, and integration with the electronics. Any queries so far?
No, ma'am.
So before I start designing my MEMS microphone, MEMS devices, I need to understand what are the constraints, what is stopping me from developing the MEMS devices. With that, we will actually end up with developing a good MEMS devices. So the first constraint that a MEMS device development forces on us is the geometry. Every foundry would, if they are using, for example, 4-inch wafer, they would have already mentioned you all that you can use only 10 mm into 10 mm area. So the area constraint will be provided to you all by the foundry. You cannot exceed your device size more than 10 mm into 10 mm. And they would have also told you all that the thickness of the device is 10 micrometer. So you cannot design your device for 25 micrometer and give it to foundry. Foundry will not fabricate. You have to follow the geometry constraints provided to you all by the foundry. So what are the geometry constraints? They give you area constraints and the thickness of the device. Next, based on the process flow, actually we are going through science foundries. So science foundry as a standard technology, process and other processes. So in standard technology, the sensing mechanism can be capacitive. So usually there are 3 transduction mechanism. One is capacitive, voltage, and resistance. So what capacitive does is, as the pressure is applied on the diaphragm, the device will provide change in capacitance. So capacitance changes as the pressure is applied on the device. So voltage, when the pressure is applied, voltage variation. Resistance, when the pressure is applied, resistance variance. So voltage and resistance are called as piezoelectric and piezoresistance devices, respectively, whereas capacitive comes under normal MEMS technology. Normal, it is only it doesn't have a specific name. So the transduction mechanism is capacitive, means you are going to use the parallel plate concept, capacitance concept to develop the device. So sensing or transduction mechanism also depends on the process flow that you are going through. The process flow defines whether you can go with capacitive sensing or whether you can go with voltage sensing or resistance sensing. So again, the constraint is provided to you based on the process flow. That is why it is very important for us to understand the process flow before starting our development of MEMS devices. Range of measurement, it depends on the sensitivity of the device. Okay, so whether you want to, if I apply 1 Pascal of pressure and there is a change in capacitance of 1 picofarad, then I want, if I apply 2 Pascal of pressure, I need the change in capacitance to be 2 picofarad. So what is the range of measurement that should be decided by the designer? All right. Next constraint is the yield. Now I give 100 designs to my foundry, and I need to understand how many out of 100 is actually working. So that is the yield, the percentage of devices that are alive after fabrication. So we should make sure that the yield is maximum. That is 100 out of 100 devices are working. If in the worst case, at least 95 devices are working. So we have to work on the design properly, then only the yield will be at the maximum. Next, the packaging technology. Before you go into the design, you have to decide what should be the packaging, whether you are going to use a silicon base, steel base, or you are going to use aluminum base. So based on that, whether your packaging is ceramic based. So based on the packaging, the temperature around the surrounding the sensor, the electrical signal strength, or everything varies. So before you start the design, actual design, packaging should be decided. You have to decide what should be the packaging that you are going to undergo for this particular MEMS devices. Hope the constraints of process is clear to you all. Can I proceed?
Yes, madam. Yes, madam.
Yes, ma'am. You can proceed.
Thank you. So understanding the constraints of the process, let's understand how exactly the fabrication takes place, right? Takes place. So what happens is, as I informed, we will have a silicon wafer. The silicon wafer varies around 4-inch, 3-inch, 6-inch silicon wafer. Hope all would have seen the silicon wafer, right? From the ingot, they slice the silicon wafer of different sizes, right? And usually the thickness of the silicon wafer will be more than 450 micrometer to 550 micrometer thick. Okay, so on silicon substrate, that is our wafer, we will coat a oxide layer. The oxide layer can very commonly used is silicon dioxide, right? It is very easy to oxide the silicon layer on the surface. So it will be around a thickness of 1 micrometer thick. Can anyone tell me why we oxide the silicon wafer? Why can't we directly proceed in developing the MEMS sensor?
As an insulator.
Very good. It acts as an insulator, because I told one wafer can develop around 100 to 150 sensors or actuators, right? So if by chance my yield is less, right? That means 1 or 2 devices are damaged. They are electrically leaking. If I don't have an insulator layer to the wafer, since all the devices are sitting on the wafer, if one device is leaking electrically, it is going to damage, short circuit all the devices. That means my yield is 0 now, right? It is damaged all the devices because of one damage in the device. So avoid such scenarios. Our silicon wafer is being oxidized. It is a thin insulator layer is being created. On top of that, we are going to deposit a silicon layer, right? So deposition, there are 2 techniques. One is chemical vapor deposition, another is physical vapor deposition. So based on the material, the depositions are taken care in the foundries. But what we have to understand as a designer is, what is my device layer? What is the material of my device layer? What is the thickness of the device layer, right? So that gives you an idea of how thick you have to develop your sensor. For example, here the silicon layer, it is the device layer where I'm going to develop my MEMS microphone, as I've shown in the picture here. This is the patterning of the MEMS devices for the required specification. It is of thickness 20 micrometer. So this 20 micrometer information is given to me through foundry. They have told us that they have a SOI wafer. The device layer is of 20 micrometer. Then to tap out the electrical signals, there will be a metal contact pad, and they have deposited it at around 0.5 micrometer. So this is the fabrication flow. So first we have a soy wafer, silicon on insulator wafer. On soy wafer, we deposit a 20 micrometer thick silicon layer, right? And then this particular silicon layer, which is all spread all over the wafer, should be patterned, right? I need this particular structure of microphone. That means this design should be mapped or onto the silicon layer, and that is done using a technique called lithography. Okay, so lithography means we are going to write the pattern that is being designed. Remember, we sent the GDS2 file to the foundry, and that GDS2 file will help the foundry people to map the pattern of the device onto the silicon. After mapping the device onto the silicon layer, the unwanted area, can you all see here? The silicon is removed from these places, right? So the unwanted area will be etched. So that the removing of unwanted area is called as etching. So basically there are three processes for micro fabrication. First one, deposition, lithography, and then etching. So these three processes are used to develop your MEMS devices. So usually there are two techniques, generally used two techniques. One is called as bulk micro machining. Another is called as surface micro machining. In bulk micro machining, what we do, we have a silicon wafer as shown in the picture, and we are trying to remove the unwanted part of the wafer itself, right? For example, there is a silicon wafer here, and we are depositing a silicon layer, but I want this silicon layer to move, right? If I do not remove the silicon wafer from the bottom, this cannot move. So in order to make the device layer move, I have to remove the part of wafer away from the silicon membrane. So I am micro machining the wafer itself. That is called as bulk micro machining. In surface micro machining, what happens? I have a substrate, I deposit a device layer, and I am trying to pattern the device layer. I'm trying to remove the unwanted layer from the deposited top layer. So that is called as surface micro machining. So there are two types of technique, bulk micro machining and surface micro machining. Usually we go with both the micro machinings. It is called as hybrid micro machining because once we pattern our device layer, it should be released so that it can move freely back and forth, right? So both the techniques are used in developing the MEMS devices. So let's understand how to fabricate MEMS cantilever beam. Okay, cantilever beam is a normal beam which will be fixed at one end, and it is free to move and on the other end. So when it is fixed in this particular end, completely fixed, that means it cannot move from this end, whereas the opposite side it is free to move. So when I apply a pressure on the cantilever beam, it starts to deflect, and when I remove the pressure, it comes back to the original place, right? So this is a mechanical element. It is a beam. It is called as cantilever beam because it is fixed at one end. So how do I proceed fabricating it? So we will have a silicon wafer. On silicon wafer, we are going to deposit a silicon dioxide. We insulate the silicon wafer, right? After insulating the silicon wafer, we are going to apply another layer, which is our polysilicon material. Okay, it can be silicon or polysilicon. And on top of polysilicon, we spin coat photoresist. Why photoresist is the part of lithography. By coating the photoresist, we are going to start patterning the device layer, right? So can you all see the black line on top of photoresist? This is called as mask layer. So wherever there is no mask, UV light passes through the photoresist. Wherever there is a mask, UV lights are not allowed to pass through it. By this, what happens? The photoresist which is getting exposed to UV light becomes soft, and the photoresist which are not exposed to UV light becomes hard, right? So after I expose the device to the UV light, I remove the layer which becomes soft, right? So the photoresist is helping us in windowing the material, right? So after I remove the unwanted photoresist, I am going to etch further and remove the device layer, right? So this is silicon dioxide layer. It is being removed. And after removing the silicon dioxide layer, I am going to deposit a polysilicon material. So we can see here the polysilicon material, it is uniformly deposited on top of silicon dioxide. And the area where the silicon dioxide is not connected, it is going and sitting on the silicon wafer directly. And then again, it is deposited on the silicon dioxide. Now, if I remove the silicon dioxide completely below the polysilicon, the cantilever beam is released, right? So when I apply a pressure, one end of my cantilever beam is fixed, another end is free to move. When I apply the pressure, the end that is free to move bends. So this is how we can fabricate the cantilever beam. This is a very good example of three fabrication flows: deposition, lithography, and etching. So after understanding how the fabrication of MEMS devices work, let's understand how exactly electromechanical coupling occurs, right? How mechanical systems are capable of producing electrical signals. For this, I have taken, since our transduction mechanism that has been supported by standard science foundry is capacitance, we only concentrate on capacitance. I'm not going to elaborate on piezoelectric or piezoresistance, because we are going to work on capacitive transductions, right? So as we know, capacitance, we will have two parallel plates separated by a dielectric. So the parallel plates, one parallel plate will be positively charged, as I've shown in the figure here. One parallel plate will be positively charged. Another parallel plate will be negatively charged. When I apply a potential difference between these two parallel plates, there will be a capacitance. So when the top plate and bottom plates are there in their original places, and if I measure the capacitance, and that capacitance is called as base capacitance, right? So the same thing has been shown here. How now this becomes mechanical is that I have a top plate, I have a bottom plate. Both the plates are separated by a distance. Bottom plate is completely fixed. That means it cannot move on any application of pressure or force, right? And top plate, the four edges of the plates are fixed, so that when I apply a pressure, the top plate will have center deflection. It deflects from the center. So what happens? Bottom plate is completely fixed. Top plate is fixed on all the four sides. It is capable of moving in the center. Mechanical concept, right? Apply the pressure, plate moves. Now, what is the electrical concept? I should have a parallel plate capacitance scenario. Top plate is positively charged, bottom plate is negatively charged or grounded. I apply a potential difference. There will be a base capacitance until the top plate is moved. For example, if the base capacitance is 10 picofarad, if I apply a 1 Pascal of pressure on the top plate, top plate deflects. Initially, it is 0 micrometer, maybe it moved 1 micrometer. After it moves, there is a change in capacitance because capacitance depends on the gap. C is equal to epsilon A by D. D is the gap between the two plates. As the gap varies, there is a change in capacitance. So this is how electromechanical system under transduction of capacitance mechanism works. Your mechanical element, which is the diaphragm, is capable of now producing the change in capacitance. Now, this change in capacitance can further converted to voltage using the integration of electronics. Any doubts so far? All are able to understand the concept?
Yes, madam.
Thank you. Any queries? Okay. So when I request the participants to mute yourself if there is no query. So if the movement of the diaphragm is along Z direction, that is out of plane, then I can go with the parallel plate capacitance concept. If the movement of the diaphragm is to in axis, okay, that is X direction or Y direction, then I can go with something called as comb drive finger concept. Okay, so there it is again a parallel plate concept. But based on the movement of the diaphragm, the parallel plates are arranged in either X direction or Y direction. And if there are n number of parallel plates, then it looks like a combs, right? Two combs joined together. So that is why the name is given to it as comb drive fingers capacitance. But the working is same. The change in diaphragm movement will give you change in capacitance. So if you have to understand the complete MEMS development, then we have to look into this picture. Here there is a MEMS sensor with the silicon membrane that is being integrated with the MOS transistor. So this is how a complete MEMS devices are developed. This is the sensor that is being mounted on a package, and this is the complete package of the sensor. It has a pressure port, the port which can allow the pressure to travel inside the sensor to vibrate the membrane. So with this basic understanding of MEMS device design fabrication technique, we will understand what we have to follow, right? What process flow we have to follow to develop our MEMS devices. As we are going in support of Science Foundry as a process flow which is called as SOI standard technology. SOI stands for Silicon on Insulator Standard Technology. It would have already given to you all what is the substrate, what is the device layer, what is the metal thickness. We have to just follow these and develop our MEMS sensor. So the silicon substrate is of 400 micrometer thick. There is an oxide layer of 2 micrometer. The silicon is of 25 micrometer thick. Okay, so they are going to deposit 25 micrometer thick device. So we have to develop a MEMS sensor of 25 micrometer thick. And the metal layer is of 0.52 micrometer. So our device that we are going to develop will be of around 25 micrometer thick. This is about the thickness information. And then the area constraints. So every designer will be given a chip size of 11.15 mm into 11.15 mm size. But the design area That is, your MEMS devices can occupy 9 mm into 9 mm area, because they require some spaces for contacts, right, to tap out the signal, and there should be spacing between one chip to another chip. So keeping those constraints, maximum area we can occupy in the given wafer is around 8.5 mm into 8.5 mm. So our area constraint, given geometric constraints given by Science Foundry, is area should be 8.5 mm into 8.5 mm, and the thickness of our device should be 25 micrometer. Very important for us to keep this to keep in the mind, right? Any queries?
Madam, can I ask the doubts in the end of the session, madam?
Okay, sir.
Okay.
So with this, I wanted to just share one more PPT with you all. That is the microphone, gunshot microphone project that we executed for ARD DRDO Pune. This I am displaying just for our understanding of how exactly we have to start understanding to develop the MEMS sensor. Okay, so there were few objectives and yeah. So we took an inspiration from a fly, which is Ormia orchia fly. The study was carried out by a university called Austin University. Okay, so they actually studied the hearing organ of a fly, Ormia orchia fly, and they converted the hearing organ into a mechanical equivalent, which was helping us to develop the MEMS directional microphone. So we researched this, and we have taken this as an inspiration to develop our MEMS microphone. This particular Ormia orchia fly has two diaphragms. One called as left diaphragm, and another is called as right diaphragm. And then whenever there is a pressure, a sound pressure from left direction, the left diaphragm will vibrate more than the right. Whenever there is a pressure from right side, right diaphragm vibrates more than the left. So this because of there is a mechanical coupling between left and right diaphragm. So this is the beauty of the hearing organ of Ormia orchia fly, and the separation between these two diaphragms are just 500 micrometer. With that only it is capable of accurately detecting the direction of incoming sound waves. So keeping this mechanical equivalent modeling of Ormia orchia fly, we developed a MEMS microphone similar to the Ormia orchia fly. It had two diaphragms. These diaphragms are responsible of sensing the incoming sound waves. So if there is a sound pressure from right side, the right diaphragm will vibrate more compared to left. So when this right diaphragm vibrates, when it deflect without deflection, there will be a base capacitance. This is the comb finger structure that is used for sensing the deflection. Initially, with no deflection, there will be a base capacitance. When the diaphragm deflects, there will be a change in capacitance. So change in capacitance is the sensitivity for us to detect the direction of the incoming sound wave. So if there is a pressure in the right side diaphragm deflects more compared to left. So there is a change in capacitance more in right side compared to the left side. So difference in right side capacitance and left side capacitance gives us the overall sensitivity and direction analysis. So this is the design that we have done. What is the constraint for us is we have to detect the sound from the gunshot, and we took the frequency as the signature. We have wanted to develop a MEMS microphone which can detect the signal at around 2.5 kilohertz. That is the frequency of the gunshot event. It has to vibrate more when there is a 2.5 kilohertz signal hitting the diaphragm. So we did few analysis. One is the displacement analysis. Another is capacitance analysis. Our base capacitance was 2.3 picofarad. And then on the application of pressure, there is a change in capacitance of around 1.68. And we calculated the total sensitivity of the capacitance. We also understood the frequency through simulation. So frequency was around 2.1 kilohertz, very near to 2.5 kilohertz. So we fixed all the dimensions. When we try to see the dimension of the devices, the device thickness was constrained through fabrication. They told us that it is 20 micrometer thick. Area constraint, again, we had 9 mm into 9 mm. So in that, we designed the diaphragm area to be 1400 micrometer into 1420 micrometer. So these are the device dimensions. And these are the response that we got through simulation of the device. For that dimension, I got a resonant frequency around 2.5 kilohertz. The time response analysis was also taken care. And then we modeled the device. After analytically modeling and simulation results, both showed us that the dimension that we fixed is giving us the resonant frequency of around 2.5 kilohertz. So after that, we generated the GUI file using Clevin tool. This file was transferred to the foundry. They used the soil MEMS process, which is now called as a standard technology process. It is the same process that I have explained to you all. And then the fabrication happened. These are the SEM characterization of the device. So we can see that the comb fingers are released properly. The anchors are released properly. This is the complete image of the device. So this is the fabricated device example. After fabrication, we went with characterization, and we can see that around 2.4 kilohertz, there is a maximum displacement of the diaphragm. This is what is required. This is the design specification. The diaphragm should deflect maximum around 2.5 kilohertz, and it is happening exactly even after the fabrication. After that, the device was packaged. So this is the base of the package, 8-pin package. And this is the cap that you can see in my hand that will be placed on the package. Before packaging, we have to wire bond. The pins should be connected to the contact pads. So this is called as wire bonding. And then that is how the complete sensor is being developed. This is just to motivate you all to take the device forward. So with this, I end the session. Any queries can be asked.
Good afternoon, ma'am.
Good afternoon, sir.
Yeah, this is Sandeep Agnihotri here.
Hello, sir.
Yeah, I just wanted to know, because in the first session, there was also talk about using tools which are open source, like the kind of OnScale or something, because at the moment, I do not have access to console or the other ones.
That will be exactly the second session, sir. In the second section, we will give you introduction to the COMSOL multiphysics tool, and also we will let you know how you can download and install the COMSOL using iSTEM portal. Okay, it is a portal which allows us to download the softwares. We will train you on the same.
Okay, thank you.
Yeah. Before the next query, I just wanted to tell you all that in the chat box, there are two Google Form link. One Google Form link is for the quiz of the session, okay? And another Google Form is the feedback for the session. I request all the participants to please fill both the forms. It will help us in the attendance tracking, okay? So quiz and feedback both should be filled. Okay.
I'm not seeing in chat board, meeting chat, this one, link actually.
Okay, sir, I'll post it again.
Yes, ma'am. I am also not able to see that.
I have posted it again, sir.
Okay.
Is it
Madam,
visible now?
Yes, madam. Yes, madam. Before that, I
Link
have
is
few
visible.
doubts, madam.
Yes, sir.
Incoming voice call from Raj Becker on SIM.
Yes, sir. You can proceed with the query.
Yes, madam. Just a minute, madam. So, madam, the Google form, I think it is asking for permission, madam.
You need
Okay, sir.
permission.
Okay, okay. I'll.
Madam, can I ask the doubts, madam?
Yes, sir, please.
Madam, the first question, madam. So, the word foundry, whether it is applicable only to the silicon growing foundries, or else it is also applicable to MEMS fabrication plants.
Sir, I didn't get your query. What
Actually,
you're
the
trying to-
people are using this word, madam, foundry, frequently.
Huh.
The foundry is only to be used for that where the silicon is growing. The like the Chakralski process, the foundry will be there, no, madam.
Huh.
That place is called foundry, or else the MEMS fabrication place is also called
No,
as
no.
a
MEMS
foundry.
fabrication, where the MEMS devices are fabricated, that is called as foundry.
Okay, okay, okay.
Yes.
And
So
the
can you
second
check the
question,
feedback form? Is it,
just
are
a
you
minute,
able?
madam. Just a minute. I will try.
Ma'am,
Yes,
only
madam. Now it is
feedback
open.
form is working. Other form is not working, ma'am.
Yeah,
Some
I
other
will.
work it is still need permission.
I will access. I'll give the access.
Another
Please
question,
check
madam.
now, sir. I guess
Yeah,
even
now
quiz
the
is
form
working.
is opened, madam. Now the form is
Okay, sir.
opened.
Okay.
Just a minute now.
Yes. Quiz also is open?
I did not check it, madam. So I'm
Yes, ma'am.
filling this.
Quiz is open, ma'am.
Okay, sir. Thank you. So certificate will be shared based on the attendance, quiz and feedback that we share. So I request all to fill the quiz and attend feedback.
Form is submitted, madam. What about the quiz, madam? I'm not able to see that, madam.
What, sir?
Quiz, madam.
Quiz.
Yes, madam.
I guess it is open now, sir. It's open now. People are
Excuse me,
responding.
ma'am. Hello.
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 Ma'am, the thing is the email ID which I registered for is different from my, like the form is accessible in Gmail, but there is no linkage for my like name with the email ID. How it can be mapped?
Okay.
So
You
because there is no
don't.
option to write email ID, and it's my Gmail default, but I registered from a different email. So is it okay if I?
No problem, sir. You can answer the
Thank you.
quiz.
Uh,
मैम ने अभी तक मुझे भेजा नहीं है मार्कशीट, अनलेस दिव्या मैम कैन शेयर, मैं कुछ नहीं कर पाऊंगा। मैंने लिख के रखा है, मैंने बात
Hello,
Yes, ma'am.
ma'am. I have one doubt.
Yeah.
Ma'am, most commonly we are using silicon substrate for MEMS fabrication.
Right.
Is there any other substrate can be used it as for this MEMS fabrication?
Actually, now silicon is being there are many researchers, even IIT Madras, they are going to invest around 150 crore funding on finding out an alternative for silicon, and the alternative for silicon is now diamond pump. They are going to grow diamond that will have electrical properties to match as silicon to and to make it as flexible as silicon to be as a substrate.
Okay, ma'am,
Research
but
is
it is,
going on.
yeah, but the availability and the cost of
Abundance is silicon. Yeah.
okay, okay, ma'am. Thank you.
Yeah.
Hello, ma'am.
Yes, ma'am.
I have one more doubt.
Yeah, ma'am.
What are the other features to consider one material as a substrate for this MEMS fabrication?
Basically, substrate is not a worry for us because substrate just acts to hold the device. Okay, it is just a like plate to hold the device. Substrate is more important if it is when the device is getting integrated with electronics. So electronics needs electrical properties, right? So like CMOS transistors, they need we need to apply electrical signal. They have to charge and they have to amplify the signal. So when the integration happens, the platform for the platform to be same as both, MEMS devices are developed on silicon substrate.
Okay, ma'am. Thank you. Thank you so much.
Ma'am, see the complete lecture schedule basically.
Lecturing for today's session is done. I request all of you to please fill the quiz and feedback form. And if no queries, we can end the session.
ma'am, I'm Dr. Ashutosh from Presidency
Yes, sir.
University.
Yes, sir.
I have one query. You
Please,
have
sir.
talked about the fabrication. Ma'am, see, I have worked on a piezoelectric energy harvester using a cantilever structure. I have
Okay,
done
sir.
the simulation on a console. The
Yes,
problem is that whenever I tried to get it fabricated through ILUP, IC Bangalore program, but the problem is that whenever they are using a community chip, they are using a SOI method where only silicon layer would be there. Other, if I want to deposit multiple layers, that process they are not able to support actually. So any other way to do something?
Sir, that becomes in community chip. What we take care is general development of MEMS devices. So
Yes, ma'am.
SOI supports the platform of general development. When you go with the piezoelectricity, you have to go for customized fabrication process. You can have your customized fabrication process flow, and then you can approach INU if you have the
Ah.
funding.
Correct. I asked them, but they asked about lot of money at that time. So we have
Yes,
not
sir.
fabricated. They
Okay.
asked around 5 lakh rupees for the fabrication.
Yes, sir. Yes, yes.
Because the
You,
funding was not
if
there
you
with
are
me at that
if you
time.
are having a specific fabrication flow, then you have to have a customized fabrication process.
Yeah. Okay. Okay. Ma'am, in this entire session, I have seen that we are going to talk about cantilever and all those things. So, do any particular kind of application based we are doing some here actually?
Yes, sir.
Something like
In the upcoming sessions, first we will introduce you to COMSOL and how to access the COMSOL tool. Then we will train you on how to simulate the design and simulate the cantilever beam, axillometer. So we are going to take you to the level of designing MEMS axillometer.
Okay. Ma'am, one last question.
Yes, sir.
Ma'am, we are using COMSOL. We are going to download from iSTEM. Okay, so that version would be a full version, or so if we are doing through that one, we can publish some our papers
Yes,
also.
sir. Yes, no license issue will come. We can publish.
Only thing that we have to this one give the acknowledgement to the iSTEM, something like that.
Right.
Right.
Yes. Yes. Yes.
Okay. Thank you, ma'am.
Thank you, sir.
Excuse me, ma'am.
Yes, sir.
Ma'am, you have showed that cantilever beam, no, madam.
Right, sir.
That cantilever beam is fixed in the supporting structure. When we fabricate the cantilever, we have to include that support structure also.
Sir, that I will display it again.
Okay.
So that is the beauty of fabrication.
Hmm.
If you can see here, we have a soy wafer.
Ma'am, screen is not visible.
Okay, one second.
Yeah, now it is visible.
Yeah. So we have a soy wafer here, right? So we are patterning a portion of silicon dioxide. We are removing a small portion of silicon dioxide. Okay. And then we are depositing polysilicon. So what is happening? Polysilicon is being deposited over silicon dioxide, but there is a small portion where silicon dioxide is removed. So it is getting attached with the wafer.
Okay.
And then there is a polysilicon. So when we remove the silicon dioxide, cantilever beam is released all over except the area where it is connected to silicon.
This is considered as that supporting structure.
Supporting structure, yes.
Okay. And another doubt, madam, in
Yes,
that
sir.
capacitance sensor, madam. So
Yes,
the
sir.
top layer is anchored in all the four sides, right?
Yes,
Where
sir.
it is anchored, madam?
Sir, again, the anchoring, whenever we talk about anchoring, it is the device layer getting connected to the wafer.
Okay.
So it is the same
like
same
cantilever.
process, yeah, like this.
Okay. And prior to the slide, madam, I think slide number 14. No,
Yes.
madam. Before this one, madam, I think. No, madam. Yes, you have to come back, madam. In my notebook, I have noted as slide number 14. Next, madam. Yes, madam. Yes, madam. This one,
Yes, sir.
how this thicknesses are uh, taken, madam, each layer.
Okay. Sir, actually what happens in the foundry, they will have a soy wafer and then they will try to deposit a material on the soy wafer. So the what material they are going to deposit is the silicon material. Okay. So silicon materials are usually deposited a technique called LPCVD, low pressure chemical vapor deposition. Okay. Polysilicons and silicons. So based on the time the silicon gets deposited. So if I keep it for 1 hour, maybe it is depositing 10 micrometer thick. If I keep for 2 hours, 25 micrometer thick. So time optimization decides the thickness at which the silicon is grown. So
Okay,
that
okay.
thickness information is given to us through foundry.
Foundry. Okay, okay.
We doesn't have any control over the thickness because they tell us
Ah.
we are going to deposit the layer for this time, this thickness.
Okay, 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 madam. Okay.
Hello,
Okay,
ma'am.
madam.
Yes, ma'am.
As part of this course, is there any chance to get any hands-on training in
Yes, ma'am. Yes.
this?
After the second session, all the other sections are hands-on. We are going to get trained on using COMSOL and also how to model and simulate the device.
Only the simulation or have any practical sessions?
No, ma'am. Actually, as I told, MEMS is through foundries. Foundries requires more than 100 crore facility to develop the devices.
Okay.
So, yeah, that is the constraint.
Any
Ma'am, if you
basic
want to
means
visit, ma'am, you can go to the Sense building. There they have the
Sense,
foundry
yes, sir.
actually.
There is a clean room
Okay.
facility.
Yes, yes.
All the MEMS devices are developed under clean room. When I call a room as clean, there are classes, class 100, class 1000. So class
Yes.
100 means there are only 100 nanoparticles,
Yeah,
not
they are
more than
maintaining
that.
100 nanoparticles.
Yes, sir. Yes. So because there are microstructures, there are possibilities of nanoparticles getting deposited in between the release, damaging your device. We need to develop these devices in the clean room. And clean room facilities are facilitated for more than 100 crore. So in Bangalore, we have Sense IIC, Bell Laboratory. So these are the CMTI has clean room facility, and Sitar DRDO near KR Puram. So these labs have clean room facilities.
But ma'am, access is only for IISc
Sorry, sir?
for academic user. The access is only at IISc or all the labs?
No, sir. We can approach any one of the lab. All are
Sir,
always extend the support to.
so you have to pay to get it fabricated. That's it.
Right, sir. Right. Each batch production fabrication takes around 5 lakh to 10 lakh. Minimum. Any further queries?
For the discussion, ma'am.
Yes, sir.
The characterization of the sensor you developed for DRDO, did you
Yes,
do
sir.
it or they did it at their?
Sorry, sir.
The characterization of the sensor that you have developed for DRDO,
Yes, sir.
was it done at your, through you or through the DRDO itself?
No, sir. The characterization should be carried out by us. And the characterization facility we used is CMTI Bangalore and IIC, Indian Institute of Science.
Okay.
The device was fabricated at IIC. The wafer level characterization was carried out at IIC, and device level is carried out at CMTI Bangalore. We have to look into the facility where the lab that provides us the facility, and we have to characterize. So happy to be connected to you all. I guess we will have a wonderful journey through this training. Thank you all for participating in the first session. I request all to fill both the forms, and I'm ending the session now. Thank you all.
Thank you.
Thank you, ma'am.
Thank you.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.